Now I'd like to welcome our next speaker, and he's a veteran because it's his 5th code dive. So this is code dive number 5, and Andrzej has been with us since the very beginning. Andrzej Krzemieński has been a software developer since 2004. He works mostly with C++ in commercial software, which includes life critical and high performance systems. He's a member of the C++ Standards Committee and a Boost developer at the same time. And as any self-respecting developer, Andrzej writes a blog. I would tell you the address of the blog, but I forgot it, so I'm not going to. If it's meant to be, you'll guess it, right? Haha, yes, that was a joke. Thank you very much for not getting it. And yes, so Andrzej is, you know, he's the guy who didn't know the password and the dongle thing and so on. And interestingly enough, his talk is called Handling Function Failures. Let's warmly welcome Andrzej Krzemieński.
Thank you. Am I on? Yeah. So yeah, I confirm what Rafał said. I was there 15 minutes ago, and it all took place. Yeah, and one of ways of handling failure is to find someone to fix it. So thanks for coming, everyone. This subject about handling failures is very dear to me. When I started coding for real, when there was serious responsibility involved, I was in desperate need to get some guidance on how to do it. And there was none, actually. The only thing I would get is just throw exceptions and be careful because it can terminate your program. And even until this day, I was not able to find some good guidance. So I digged on my own for a couple of years, and I have now something I can present that I believe will give you some insight into the problems related to handling failures, so that you can make more informed choices. And the first thing to successful handling of failures is to be able to distinguish two categories. There are two reasons why our programs get into a disappointing state. One is that there is a disappointing state in the environment, and this is reflected in the code. And the other one is that we have a bug in the code. And there is different ways of handling either case. This is how a bug looks like. I'm passing too big an index to a vector. And it is a failure in some sense, a failure of a programmer to understand the API. But this is not what we will be discussing today. This is an important topic. It needs to be addressed. There's many ways of addressing this, but we leave it out of scope. What we call failure in this talk, or error, is when the function liked our arguments, it promised us to do something, and then, because of different reasons, probably related to environment, it concludes that it cannot do it. And it needs to report it, we need to take some actions on it. And this is what we'll call failure or error in this talk. And we start with an example of error handling through error codes. This is a piece of code I found on the internet. This is instructions on how to write a HTTP client in C. There I changed it a bit so that it's more C++-like, a bit shorter, but I left the error handling intact. And basically what it does, it tries to obtain a file descriptor. If it works, it will try to identify the host by the name. If it works, it will try to connect to the server using the socket. If it works, it will write some data to it. And if that works, it will read some data back, and it will display it to us. And the reason I need to put those arrows and text, that there's another failure to be handled, is because this cool stuff, the most important stuff, gets lost in those if statements and error handling statements. Of course, in the previous slide, the die means display the error message and exit. We cannot do it. This works well for example application, but on a server that needs to run for months, we cannot afford to die. No one can afford to die. And we will be returning from the function, and we will return some error code, which gives an information to our callers what actually happened, because maybe this can be addressed in one way or the other. So what we can, well, this already illustrates a number of things, that if statements, returns, and integers are enough to handle any failure in the code. And handling code is nothing more than taking different branches. Like you communicate with the server in a different way when you cannot obtain a file handle or open a socket. You can also see a certain pattern in this code. This occurs time and again. I'm doing some interesting operation, then I'm checking if it perhaps failed, and if it did, I'm doing the premature return. And again, another thing to observe here is that error handling is usually about doing premature returns, about skipping some operations, because the subsequent ones no longer make any sense. And because this, let's go back again, this pattern occurs time and again in every function, C++ exceptions address this directly. Only because you put one instruction under the other, it means that do B, in our case, depends on the A, and we don't want it to be executed if the previous one fails. We don't have to do any wrapping and any explicit ifs. They are there, hidden, but only because the one instruction is below the other, it means it depends on it. If do A fails, we don't want to execute db, we want to cancel it. If we cancel it, we also want to cancel the next operation, do C, because it no longer makes sense. And we want to annotate our doX function as failed. And this is not executed in void, it is called in another function. If it fails, the subsequent functions depend on it, they cannot proceed, we have to cancel them also. And this is what exception handling is about. Describing this dependency of operations, the success dependency or failure dependency, and then starting this cancellation cascade, which goes on and on until at some point where we really know what we are doing, we are ready to stop this cascade. Like in a server, in a main loop, when we are processing one request and it fails for some reason, we can just eject the operation and go with another one. And this illustrates yet another thing, that why we are given advice that we should not catch exceptions in random places. You usually don't want to stop the cancellation cascade like this only because you're afraid of terminating something or whatever reason. You don't want next operations that depend on us to continue. You want to cancel. And this failure cascade or cancellation cascade is the coolest feature of exceptions, the most important one. There are others. Like you can pass arbitrary information to the guy that will actually handle the exception. You don't waste the return channel, so the functions can still return the computed results. And this works for functions that do not return at all, like constructors. The logic for handling errors is separated from the normal logic. So we are not cluttered with our code, it isn't cluttered with those if statements. And if we forget that our functions can fail, we usually get good default, because the cancellation cascade will be started for us, and it's usually that's what we want. But the exceptions come with a cost. You pay the overhead in terms of the space our program occupy and the execution time. any function can throw any type of an exception. So we'll be using some type of type erasure. We will need to use heap memory. So either we allocate and we pay for allocations, or we reserve some memory per thread, because stacks and stack unwinding is done per thread, to keep a stack of exceptions, because we can handle more than one exception in one thread, believe it or not. And this costs, even if you turn the exceptions only in programs that communicate through error codes, only because you turned it on, your program size increases. Plus, in order to get the erased type back, you have to do some runtime type identification. The structures get bigger, you get virtual function pointers, and you pay this meta information about the types needs to be stored somewhere, you will pay. Only because you potentially use exceptions. Now, when you actually report failure through exceptions, there is another cost to be paid. We have to do this RTTY stuff, examine the pointers, what it maps to, which handler to check. And some people report the overhead increases even in 2 or 3 orders of magnitude. And there are other reasons people choose to use error codes. Like every control path that there is in a program is explicit. When you are reviewing the code, you can see it. It's somewhat contradictory to having it implicit and code being short, but some people like it this way. And you only use ifs and returns, so it's easy to learn when you're starting. And not every programming task falls into this category of failure or success dependency. Sometimes there are more complex control flows, and then exceptions cannot help you, and they even disturb you. And there is a contract related to exceptions that programmers and compiler vendors know, that apart from the constant overhead, you will get no runtime overhead when you don't report failures from your functions. And you will pay potentially huge cost when you actually report a failure. And this affects the advice that programmers are given, that you should be throwing exceptions where this overhead is acceptable. This is, for instance, when you are a server processing customer request. At some point you realize that you will not be able to do it, you will disappoint your customer. You can add to this disappointment but by having him wait another millisecond. And going back to the example, you will have noticed, it's at the bottom of that, I have implemented a memory leak. Not a memory leak, but a resource leak. It wasn't there when we were dying, but now that we are returning, each time when something goes wrong and we do the premature return, we leak a file descriptor. One leaked file descriptor is not that much, but if this continues, upon each failure to communicate with the server, we are leaking one file descriptor. The system still thinks we are using it, and at some point we will not be able to allocate a new one, and bigger problems occur. Because this is a second popular situation that occurs in our code, that some operations can be classified as acquiring resources from the system. And if we do this, we have to release it, this resource, even if something fails in between, even if we want to cancel next operations, this one must not be canceled. And if we want to have a code that doesn't reflect all the paths explicitly, but lets us focus on a business logic, we need an idiom that says, try to acquire the release. If it fails, yes, start the cancellation cascade. If it succeeds, schedule the release of the resources, no matter what happens, whether we cancel or not. And this is exactly what RAII, resource acquisition is initialization, is for. If you work with the language, if you acquire your resource in the constructor and release it in the destructor, this is the semantics of the destructor is exactly what you need. It will be invoked no matter what. And this is useful not only because we have exceptions and now there's something dangerous, but even if we returned errors through error codes. C programmers are often taught not to have many, that you only have one return statement in the function. And this is because if you have more of them, like early returns, you will get the resource handling wrong. You will not get it right. You will forget all the places where you need to do this. And this illustrates what Sean mentioned in the morning talk, that while we are talking about exception safety in C++, we should be actually talking about failure safety, because whatever method of of handling errors by canceling some operations you choose, you will run into this problem, and you have to be prepared what to do with it. Now, destructors can be used and abused for whatever you like, but they were specially designed to release resources. And if you play by the rules and use them only for releasing resources, all things become simpler. Like, you immediately get why you are not supposed to throw from destructors, and it has nothing to do with calling or not calling terminate. Let's see it by example. I am doing some mathematical computation. I take two integers, x and y, and I'm producing a new integer z. And I need some system resource to perform this computation. And this can fail for a number of reasons. First, the acquisition of the resource can fail. If it fails, I cannot compute my z. My callers, who need this z, will not be able to move on. They have to be cancelled. So I'm starting the cancellation cascade. I throw. If acquiring the resource succeeds, I'm doing the computation, and this computation can also fail, also because of the resources, because I'm communicating with the resource. If it fails, I cannot produce my z. My callers cannot move on. I need to start the cancellation cascade. But now, suppose I've computed the z. I'm releasing the resource to the system. And this can also fail for a number of reasons. Communicating with the system is likely to fail. But even if it fails, I have my z to return. I have done my job. My callers can continue. They can do their job. I have left some mess behind, but there is no reason to start the cancellation cascade. Sooner or later, this will spoil somebody else's job, but it is their problem. They will report failure to do their task, not us. It is nice to detect every strange situation in the system as soon as possible, and if you need it, you can use other means, like some global stuff for informing of these things, or using logging or whatever else. But do not start the cancellation cascade. You have you delivered what you promised. And let's see another example, how it maps onto using file streams. I have a function, suppose it's a word processor, and I have a function that saves my work to the disk. And we call it save, but we all know it really means either save the data to the disk or inform me that you failed. Because if you do, I know what to do manually. I will copy and paste it to the clipboard. I will handle the situation, but I need to be informed. The first attempt, you will find it in the tutorials, how to store your data in a disk. We are opening a file. We are buffering some data. And at the end of the scope, it is flashed to the disk. Now, if whatever happens wrong in this, if anything goes wrong in this code, like buffering the data, nothing will happen, because standard streams do not throw exceptions by default, unless you tell them to. So we have to tell it to throw exceptions. We have to start with a dummy file stream, which cannot fail. Then we have to tell it what exceptions to throw, and then we have to open the file. And now, if the buffering of the data fails, we start the cancellation cascade. We inform our callers that we failed. They will do it manually or not, but they have a chance. But what if buffering worked, and the real job is actually there in the destructor. This is where the data is really written to the disk. What if it fails then? And standard types do not like to throw from destructors. So they will swallow the exception and will not tell you a thing. You will not even know the function will return successfully. You will not even know that there is no data stored in your disk. And this is because the destructor is not releasing resources, but is actually doing some job. And actually the most important part of the job, really doing writes to the disk, the operation that really can fail. So the correct way to do it is to put an explicit write yourself, even though it's obvious. It's obvious that the last operation we want to do on a stream is to flush the data. But say it explicitly in order to, for everyone to see that this operation can be cancelled if the previous one fails. And also, we want to show that this operation can start the cancellation cascade if it fails. And now, in the destructor, the only thing left to do is to release the file descriptor to the system, which is less likely to fail. And even if it fails, we've done our job. We saved the data to the disk. We leaked some resource. It's better than any other alternative that we have. OK, next item. What information should we store in exception and carry to whoever handles the error? And the answer to this question depends on whether we are handling the error locally or remotely. This is how local error handling looks like. I'm using a standard library function for copying a file from one location to the other, and it perhaps fails. If it fails, I get this file system error. I can read the source path and the destination path from the exception object. But I don't need it because I can see those names already. I chose them. So you don't have to remind me what it is. It's just redundant information. So let's see how it looks when we are handling the error remotely. This is the main server loop. On each iteration, we are processing customer requests, and it can fail for thousands of reasons, and it can report hundreds of exception types. And at this stage, I will not be putting 100 catch statements. I will need all my exceptions to have one uniform interface. And what can a uniform interface do? It will either give me some code or some string, but nothing more. I will not be playing in trying to check whether it stores some file, which has no meaning at this level anymore. So again, I think this information is not that useful. And what people converge to is that the meaningful information that is enough for you to make some informed decisions is to tell me what component or library or domain errored, and some error code within this domain. And we have, since C++11, this standard error code type, which stores exactly that. It needs 2 registers to store a domain and a value within this domain. And if I'm writing a new library, I will provide enumeration with all possible errors from my library. Then I need to put some boilerplate code, which is quite long. So for me, it's just one comment, but for you, it will be a custom template specializations. But it's a mechanical job. And once you do it once, you can use enumeration as though it was error code. So the numeric value of this enum is converted into the value inside this error code, and the type of our enumeration is converted into the domain pointer. So there is some type erasure because we are changing a type into a value, but we get an object that is trivially copyable, and you can easily pass it through registers when you return it from functions, or can easily store it in exceptions. And if you really need to store different information about failure at different types, you don't necessarily have to use different types of exceptions. You could use boost exception, which is exactly for this. Internally, it stores something like a map of any possible chunks of information you want to stuff in. Like if I want to store information about source path, I would declare my chunk, which is from path. I'm using this error info to define those chunks. I only need to tell it what type of information it stores. And this additional struct created on the flight, I need it so that my from path is a unique type, even if I'm storing the same piece of information, like here. If I want to store a destination path also, I will be storing the same type inside, but because I use different tags here, I render two different instantiations of a template, and they will never be confused. And later on, when I'm throwing exception, or I'm temporarily catching the exception only to put some additional information, I can use this chunk I've created. It's type safe. It knows that it should expect a path, which is converted from the string. It will store this information inside the map. And later on, when I'm prepared to handle the exception, I can ask whether this particular chunk of information is stored. And if so, I can use it in a type safe manner if I really need it. So given that you can do that you don't need different types of exceptions to store different information, how many exception types do you really need? And my practical answer to this question is you will need different type of exception for a different level at which you want to handle them. Like I would have one exception to kill the application, perhaps when I'm out of memory. Another type of exception to kill one transaction from my customer while processing, and perhaps another one to kill some smaller sub-operation within transaction that can be safely rejected and my transaction still continue. And that's it. Okay, next item. When should I throw exception? Is not being able to find an element in a collection a failure or not? Or not being able to convert A to an int, is it a failure yet or not? And the practical answer you will be given is that you don't throw exceptions when you are pretty sure it will be handled the next level immediately. Because you don't want to pay for the overhead of communicating exceptions. Or to put it the other way around, if you are throwing the exception, you need to be prepared that it will unwind big portions of your program and perhaps even kill it. And perhaps this advice would be different if throwing exceptions were cheaper. Now let's see different choices for the interface for a function that converts a string to an int and how it works. This is the interface that Boost Lexical Cast has. You give me a string as an input, and I give you the converted type as output. And if it fails, I throw an exception. And I really hate this interface because every time I need to do this, it's usually when parsing configuration files or the input from the customer XMLs, I'm handling this error locally. I'm usually starting with some good default value in my configuration, say for port. And if it doesn't work, it's okay. I know what to do. I want to go with the default value. I want to ignore this failure actually, consciously, but I have to pay the cost for RTTY, matching the handlers, needlessly. Or here, if I want to go with default value, if I cannot read it from my configuration file or whatever, I don't want to pay the cost for RTTY. Or perhaps I want to throw an exception, sometimes I do, but I need to throw a different type. And now I still have to pay for RTTY for catching the first exception, only then to throw another one. And again, this cost doesn't need to be there. Someone made the choice for me that he wants to start this exception stack unwinding with his exception. So I started to like this interface better. You provide some storage for the converted to type, and I get it as the output parameter, and give you a true/false answer whether the conversion worked or not. And now I don't have to pay for anything. I know that it fails. I don't even need to know the reason because I know the reason. The input was wrong. and I want to go with the default value. Or I want to throw an exception, but my exception, not yours. But you can say that I'm going back to C and to the disadvantages of error codes, because I can forget to check whether my function returns successfully or not, and risk getting into some strange states of my program. But this is not the case since C++17, because we got this no discard attribute. It was even before that with different compiler extensions, but now it's standard. It means that whenever I fail to read the result of this function, it is a compiler warning. And if I turn compiler warnings into errors, and I do, and you should also do, I get an error, and I'm forced to respond and to make a conscious decision, what do I want to do? And in a way, it is better than exceptions, because with exceptions, I get a good default if I forget. That works in 95% of the cases. But in the remaining 5% of the cases, it will do the wrong thing. And here, I get to choose. And I know better. But sometimes, I do want to ignore the failure. The fact that it might fail, because I'm starting with the default. If it didn't work, okay, my default is good. But it will still give me a warning. But this attribute comes with a standard way of shutting it down. If I cast it to void, it's the standard way of saying that, yes, I consciously made a decision to discard this error information. Doing it like this has a problem of its own, because I can forget to annotate some function with no discard. But there is a way around it. I can provide my own type, like success, which may store this bool inside, or may store this error code, but it's a distinct type, and I can annotate this type as no discard, which means any function that uses this type as return type is becoming no discard by inheritance. So now every function that uses this type is no discard. And this brings us close to the outcome library. But before we go there, there is one other thing I need to show you. This function convert is not marked as no except. No except false means it still throws exceptions. And it does for a purpose, because there are two reasons why a converting function can fail. One is the obvious, that you gave me the wrong input. That doesn't make sense in context of converting to this type. But there is other reasons. I may temporarily need to acquire some resource from the system, like memory, or maybe some global dictionary. And if it fails, it's random. Next time it may succeed, but this time it failed for random reasons in the system. You will not know how to handle it locally. Because some problems are inherent to the nature of your function, like conversion, and some others are very private reasons that you will not understand. The caller may not understand or be aware of. And for these cases, I want to start the cancellation cascade nonetheless, even though I'm returning a true-false answer. So yes, this is what I've said. And the same situation occurs in the standard file system library, where nearly every function comes with two overloads. This library will not make a decision for you how the exceptions should, failure information should be propagated. Maybe you don't like exceptions, maybe you want to handle your errors locally, and exceptions would not be a good fit, so you get to choose whether you want exceptions or whether you want me to write this error code parameter. But this second overload still throws exceptions. And some people consider it an oversight or a bug in the specification, but it's actually not. It's using the same reasoning. The contract behind the file system library is that it is only a thin adapter layer over your native system's API for dealing with files. If this API fails for whatever reason, you get an error code. And you will probably know what to do, because those errors are related from dealing with files. But it's also possible that this thin adapter layer fails for its own reasons. Probably it will be memory, but maybe something else. If this fails, you will not know what to do. You may not even know that this adapter layer exists. So even though you requested error codes, the errors from this adapter will be reported as exceptions. And this is by design. But there is one problem with reporting errors like this, both in my convert function and with computing the file size and every actually function in a file system, that if a failure is reported, I am left with an object in a state that is unpredictable, undesired, and likely to cause some failures if I try to use it, like file size function. If it reports errors, if it reports an error, what does it return? Like 0, but 0 means the 0 length of a file that exists. If a file doesn't exist, the 0 is not the right answer. -1, you will likely be confused. Because what we need when dealing with failures is to return either the computed value t or information about a failure, but never both. And C++ exceptions do it the right way. When you use them, you either get the value or the error information, but you cannot get into both of these places at a time. And this observation lies at the heart of a outcome library, which was recently passed the Boost review and was accepted into Boost, but is not shipping with Boost yet, but you can use the standalone version that doesn't require Boost. It is a number of tools for dealing and reporting failures in not a canonical way. And one of the tools inside is this result of t, which is like expected that this function either returns a t or returns this standard error code, but never both. And it knows which one it returned. So if I implement my function using this, I can either return my enumeration, which gets converted into the error code, which gets converted into this result of t, because it has converting constructors. And if everything works okay, I can just return my t, and this gets converted into the result of t. And this doesn't work the other way around. If I want to use this result of t as t, I get a compiler error because of the type mismatch. I have to decide what I want to do with it. And I can do a couple of things. I can call this value, which if it stores a value, it will give it to me. If it does not, it will throw a normal exception, like a system error, which stores this error code inside. So I have a way to convert it into a normal exception if I want it. I can also inspect it manually. Just ask it whether it stores a value. If it does, I can read the value. If it does not, it means it has to store an error. I can get the error. Or I can go back to this value, which also works in this context. The double check for the condition is elided. But maybe it's not that good an idea, because you confuse the readers as to what you want. But the best part of this library is to enable you to start the cancellation cascade in a way that does not require any RTTY or handlers. Suppose all your functions in the call chain use this result of t. I need to read an int from a file. This means I will have to read a string from a file, which can fail, and then I need to convert it to int, which can fail also. If all those return those result of string, result of int, I can use this macro, which is a control statement behind the scenes, which works more or less like this. It inspects the result manually. If it's an error, I return it up. If it's success, this str will represent a string which I can use. So it's not a result of string, it's a string. And I can pass it down to other functions, and they will do the same. So it's again like a cancellation cascade, but the error is returned by value. Statically, we know the type. It's 2 words, actually, 2 registers. This whole thing can be elided. and for the compilers like Clang and GCC that implement some not standard extensions, there is another macro which makes it similar to Rust's try operator, which can even be combined if you need it for some reason. Some functions do not necessarily return anything, but can still represent, they can still fail, and this needs to be represented. For this, you can use result of void. And if you just call it blind, the compiler will protest because this result is marked as no discard. You cannot just forget, not read the value. But if you do, I mean, if you encounter this error, you have to make a decision, and one decision is to use, again, this outcome try, which in this context, and the context is I passed one argument rather than two, it is resolved to something like this. If there's an error, make a premature return, otherwise, move on. So this macro is overloaded. If it takes one argument, it is this result of void semantics. If it has two or more arguments, it will additionally give you another name in the scope. So it gives you this result of T gives you a choice. It is not the function that makes a choice for you. You get to decide how you want to proceed, whether to inspect manually or start this lightweight cancellation cascade or go with the normal throw. But how do you deal with constructors, which cannot return anything? And what this library gives you is to use factory functions instead of constructors. This is more or less how it works. There will be a guts of your resource managing type. Guts are usually trivially copyable, but you don't want to use this functionality. You want some logic. The constructor, which takes those guts directly, is not exposed to the customer, so nobody will fiddle with it. The only thing that you expose is this factory function, which takes the decent parameters that your callers will understand. And you implement it more or less similarly. If you are trying to perform some system call, if it fails, you return the failure. If it succeeds, you just build this result of file. And I'm using this in-place construction in this place in order to make it work even with types that are not copyable or movable. And there may be some discomfort when you think about using factory functions instead of constructors. Maybe it's justified, but considering the alternatives, this may be the right choice here. But there are also the positive sides. When you're using factories, you can have two of them that take the same set of arguments but do different things. Consider creating a vector with the initial size and with initial capacity. Not possible because of they have identical types. No problem here. And I could not recommend this technique of factories in C++03, because then, in order to return something by value, your type would have to be copyable. Since C++03, returning by value doesn't require your types to be copyable. It's enough if they are movable, which is the case for most of the resources you handle. And it's C++17, then they don't even have to be movable. I can safely return a mutex from a function, and it just works. And I can use this factory function. This blends nicely with the rest of the library. I can just use this outcome try, and now my f is not a result of file, it's just file, which I can use. The fact that this library was even created and is getting popular, and we have more libraries like this, we have this expected, which is now being standardized, indicates that something is missing from the C++ in terms of how we handle exceptions. And the standards committee sees this need and tries to address it. This is a future development. We will for sure not have it in C++20, maybe 23, maybe 26, maybe 30, whatever. But the idea is this. you will annotate your function that it throws in a different way. It throws something, as if returning something like result of t. This function either returns a int, probably through the registers, but there is no int to be returned. It can use the same registers to return you this standard error, which will be something similar to standard error code, but with some of the problems with the previous one fixed. And you can report error with throw, but this time there is no object created on a heap or on the side. You just return it through registers. And you can use catch to check, to stop the cancellation cascade and check the error. And it works. The semantics are similar to, again, inspecting this result of t. If we get the value, we get here. If we get an error, we get there. And it's all passed by value, so you pay no runtime cost for it. It's as cheap as returning 2 integers. And that's it regarding the technical stuff. One other thing to mention is that the error handling should be blended into the design of your application, even interface, from day one. Even when at some point you are communicating with the outside world, like in my case, we are receiving requests and providing responses to the customers. There is some format to ask about the flight from one destination to the other, and there is some response format with the flights. And it is at this stage that we have to decide how we will be communicating to the customers that we didn't do what they requested of us, or that we did only part of the job they requested of us. This has to be designed. This is a part of the contract with the customers. And if you forget about it, if you neglect this, you're risking concealing the information from the customer that he may need, not necessarily the flights, but the information that something was wrong. Or you will be sending wrong information to the customer and giving the impression, perhaps the correct one, that you lost control of what's going on in your program. So the only advice for the end, or the takeaway, will be that, at least in my analysis, the failure handling is actually about expressing this instruction dependency. It's most of the time is what operations you choose to cancel, in what order and to what degree. And another one is that every error or the parts of it should be communicated to the right people, and this should be included in the design. And what particular tool you will choose for it is on you, if you handle if you adhere to the other rules. And that's it. Thank you for the talk. I hope you like it.
Thank you. We've just got some time for questions, please. Yes, over there. Where are you going? You're supposed to ask questions, not leave the room.
Thanks. So first of all, thank you very much for the talk. You mentioned the problem that you run into with outcome if you want to report errors from constructors. It doesn't really work, and you have to switch to factory functions, which is its own can of worms. So shameless plug, I gave a lightning talk at CPPCon this year where I presented an idiom that tries to solve this problem. The talk is called Fixing Two-Phase Initialization. So if you're interested, maybe check it out.
I would be glad to watch it.
Thanks.
Thank you.
Did you have a question, or was it just a comment? Yeah, okay, no. Comments are fine. Comments are fine. I can comment. I don't want to. Any more questions or comments over there? Okay.
A lot of problems with exceptions are, in fact, that they are slow to throw. And if that was not the case on your slide, you said that would change a lot. Isn't there something in community to actually make throwing blazingly fast?
there are two ways to approach it. Some people will say that how it works is fine, you just need a better compiler that better optimizes, aligns it, and it just works. Technically, you cannot say it's impossible, you cannot prove it, but so far exceptions have been there for 20 years or so, and no one was able to do it, which may be an indication that this is not possible. The other way to approach it, and I think this is what the committee is going to, is to make a certain trade-off. That you can make it faster, avoid this RTTY, if you agree, maybe it was not stressed here enough, to only throw a dedicated type. You deprive yourself of the possibility of throwing arbitrary type, so you lose something, but you trade it off for performance. And now the performance is guaranteed. You can see it immediately. Also, C++ goes into this direction that you will not add features that can potentially be optimized, and there are, but that you can immediately see that they are fast, even with all the optimizations disabled. So this is one of the functionalities which technically we can optimize, but it's not immediately clear, and the programmers cannot infer based on this, cannot make predictions.
Okay,
So.
Thank you. Just one more thing, if I may ask the audience this time. As I told you before, Andrzej is a veteran, so he's been with us since the very beginning. So it's the 5th code dive and Andrzej's 5th time. And I've been asking Andrzej to start writing a memoir or like a biography of code dive. I think he's the right person to do it. Am I right? Okay. So I need you to help me to convince Andrzej to start doing it. Okay. So I'm going to ask you, should Andrzej write a code dive bio, and you are going to answer yes, like with a very long S at the end, okay? So let me ask you a question. Should Andrzej write a bio for code dive? Really? Are you sure? Over to you, Andrzej. Next year we are expecting a draft, and Andrzej Krzemieński.
Thank you. Thank you very much.